Hello. So let's talk about the ABC Bank machine learning workflow today. And first of all, the ABC Bank project dataset contains approximately 10,000 observations and 20 features, which you can see from here. And during our analysis, we found that the dataset was remarkably clean, showing no duplicate rows and no missing values. Next, we did the EDA with a clean data set in hand. So we utilized AutoVis to conduct an automated exploratory data analysis, EDA, which we did right here. And one of the most significant insights gained from AutoVis was the identification of skewness in variables such as annual income, years of employment, and the number of children. And furthermore, our EDA involved the creation of a correlation heat map, which we can see from here. This visualization allowed us to identify strong relationships between variables, such as the correlation between age and unemployment status, or the obvious link between family size and the number of children. Next, we did the encoding categorical features. So in the project, we utilized a label encoding for variables like income type, education, and family status, which you can see from here. And label encoding converts each unique string category into a distinct integer. For nominal categories without an intrinsic order, such as geography or gender, one-hot encoding is often a superior choice. So this method creates a new binary column for each category, where a 1 represents the presence of that category and 0 is its absence. However, we must be aware of the dummy variable trap. The notebook's reliance on label encoding for its initial random forest model was appropriate, as tree-based models are generally more robust to integer-assigned categorical variables than their linear counterparts. And next, we did the standardization, which you can see from here. So for this project, we employed standardization, transforming our numerical variables to have a mean of 0 and a standard deviation of 1. So by converting features like age, balance, and estimated salary to z-scores, we ensure that the model treats each feature with equal weight during the learning process. And next, we did the PCA. So you can see from here. So in an effort to manage the high-dimensional nature of the 20-feature dataset, we applied PCA. PCA is a statistical procedure that forms an orthogonal transformation to convert potentially correlated variables into a set of linearly uncorrelated principal components. The primary goal of PCA is dimensionality reduction while retaining as much variance as possible. So in the ABC notebook, PCA was used to analyze the variance structure of the customer data. While PCA reduces complexity and can filter out noise, the resulting principal components are linear combinations of the original features, making it difficult for business stakeholders to understand why a certain credit decision was made based on a PCA transformed input. And next, we did the k-means clustering, which you can see from here. So the k-means algorithm partitions the data into k clusters by minimizing the variance within each group through an iterative process of centroid assignment and update. In this project, we utilized a clustering to create a new categorical feature representing the customer segments. The hope was that these segments would reveal underlying patterns of behavior that correlate with credit approval. However, the final analysis showed that the addition of cluster memberships did not significantly improve the accuracy of our supervised models. So this demonstrates a key limitation of feature engineering. And next, let's talk about the suitability of these three models. Logistic regression serves as an excellent baseline due to its simplicity and a high interpretability of its coefficients. In a regulated industry like banking, being able to explain why an applicant was denied is just as important as the prediction itself. So, however, logistic regression assumes linear relationships and can be outperformed by ensemble methods in capturing complex nonlinear patterns. And next, about the random forest, which is an ensemble of decision trees. It is highly suitable for this task because it can handle both numerical and categorical features with minimal scaling required and captures nonlinear interactions automatically. By averaging the predictions of 100 or more decision trees, it reduces the risk of outfitting and provides robust results. And next, about the H2O AutoML, it provides an automated low-code platform that explores a wide range of algorithms, including the GBM and deep learning models. It handles much of the pre-processing internally and ranks models on the leaderboard. So this is particularly suitable for ABC Bank because it allows the data science team to rapidly benchmark different architectures and identify the most perform performant model for customer churn and credit approval with minimal manual turning. So the performance results of the ABC Bank project provide a profound lesson in model evaluation. Initially, the random forest model showed a high accuracy of 85%, which you can see from here. And however, a deeper analysis revealed that this metric was misleading because the dataset was imbalanced, where a majority of applicants were denied. The model achieved high accuracy simply by learning to predict the majority class for almost every instance. So in banking, this accuracy trap is a critical failure. The bank's goal is not just to be right most of the time, it is to correctly identify the minority class, the high quality applicants who should be approved. So this is where metrics like precision, recall, and the ROC AUC score become essential. Now, the H2O AutoML results, which showed an AUC of approximately 0.55, which we did at the last part, indicated that our current feature set and pre-processing were not yet powerful enough to cleanly separate the two classes. This suggests that the model was essentially flipping a coin for the different difficult cases, highlighting the need for more sophisticated feature engineering or sampling techniques. The primary strength of our approach was the thoroughness of our pre-processing pipeline, including the removal of noise and the use of automated EDA. So we successfully implemented a workflow that standardized the data and prepared it for high-level automated modeling. However, the limitations are equally evident. The failure of PCA and clustering to improve model outcomes suggests that the latent information we were trying to uncover might not be present in the existing features. Furthermore, the lack of class balancing techniques like oversampling or undersampling meant that our models were biased toward the majority class. To improve these results, we should implement several advanced strategies, including addressing imbalance, data and text engineering, advanced scaling and transformations, and also hyperparameter tuning. And finally, about the real-world patterns and business implications, the outcomes of this project suggest significant patterns for real-world banking applications. The fact that age, income, and employment stability are the strongest predictors underscores a traditional robust reality of financial risk. However, the difficulty in achieving high AUC scores highlights that creditworthiness is a multidimensional problem that often defies simple categorization. For ABC Bank, the implications are clear. Relying on simple accuracy metrics could lead to stagnant growth if the model systematically denies valid customers. Moving forward, the bank must prioritize recall and the AUC score to ensure it is accurately identifying every profitable customer opportunity. And furthermore, the use of automated tools like H2 AutoML shows that the bank can remain competitive by continuously benchmarking new models against their established baselines, ensuring they are always using the most effective predictive engine available. Thank you.